Hello everyone. So we are going to continue with mathematics where we ended last time. Remember, we are looking at set laws, or rather laws on sets, and laws that we mentioned. So this is math, by the way, in case someone is thinking it's something else. This is math. So sets, and we're looking at laws on sets. Briefly, what we'll some of the laws that we talked about. We talked about number one, what is called the double complement. Okay, double complement, which is a complement is equal to, all right. So we looked at that, and then the other one that we looked at was what is called the associative law. Associative law, that is, we have let's say A intersection B is the same as B intersection A, or we have A union B is the same as B, and then what is called the commutative law. Okay, commutative law, where we say that if we have intersection B in A, we can also have A union B union C, which is equal to A union B brackets first. Then we look at the what is called the let's say intersection B C, or A union B intersection C equal to what? A union B in brackets intersection A union C. Okay, so those are some of the laws that we talked about. Then we also looked at identity law. So number 5, identity law. Okay, so identity law, what was it? Let's say if we have, let's say, empty set. Okay, empty set union set A, this is going to be equal to set A. Then let's say the universal set, and any set is going to be equal to that particular set. Okay. Then the other one that I should talk about is if we have A complement intersection B, a set and equal to set. Okay. The other one that is important, where we say that A intersection a set is equal to the set itself. Okay, things that we talked about, and then we also mentioned the De Morgan's law. Okay, that's what we want to look at today in this lesson. We want to look at what is called the De Morgan's law. So I'm trying to remove this thing on my screen. I don't know what's happening. Okay, so let's continue and look at the De Morgan's law. That is the main thing for today. Okay, the De Morgan's law. So if we look at the De Morgan's law, when you look at the De Morgan's law, this keeps popping up. Okay, so when we talk of the De Morgan's law, we can say number one, A intersection B, everything in brackets, okay, is equal to. So this once, and then if we put the complement there, we can distribute the complement to A and B, and then once we do that, the sign is going to change there. All right. Once this complement is distributed to A and B, then the sign should what? Should change. So this is going to be equal to A intersection, A complement. So since there is intersection, so it's going to be B complement. Okay, A union B complement. Now, from there, the other one that we have. Now, remember, maybe let's first prove one. Remember, we said that two sets are equal if they are what? Subsets of each other. Okay? Two sets can only be equal if and only if they are subsets of what? Of each other. Meaning that this set can only be equal to that set of each other. Okay? Now, before we can go in proving it, I want us to see if at all what we're talking about is really true using what is common to you guys, which is the Venn diagram. Okay? So let's try to use the Venn diagram and see if what we're talking about is really true. Okay? So let's say, for example, we have the universal set like that. Okay? So let's say we have the universal set. Okay? And then we have set A and set B. So A, and this is the universal set, right? And then let's say here there's 1 and 2. Then here let's say 3 and 4. Then here 5, 6, and then 8, like that outside. So now, we want intercept B complement. Intercept B complement. We should first start, okay? Let's look at the entire universal set. We should see that the universal set itself is having the numbers 1, 2, 3, 4, 5, 6, 7, and 8, right? So that is the. Now let's try to list what we list A intersection B. Okay. So what is going? A. What is set A? Set A is going to be. Remember, there is 1, 2, 3, and 4. That is set A. And then set B, there is 1, 2, 5, and 6. Okay, 5 and 6. Then what else? So that's what we have, right? That's what we have. Now let's get A intersection B. Okay. So what is our A intersection B? What is common between A and B? We can see that 1 and 2. Okay. So this is our A intersection B. If we say A intersection B, it means we have everything that is outside intersection what? Intersection B. Everything outside what I've stated in red. Okay. Outside of red. Intersection B. Okay. So let's list that. A intersection B complement then is going to be equal to, we're going to have what? 3, 4, 5, 6, 7, and 8. Okay, so that's what making what? A intersection B what? Complement. Okay, so we can see that this is what is on the left hand side. This is the left hand side of this equation, or rather of that formula that we have, right? Now, let's look at the right hand side. So what is the right hand side? Let's look at A complement. What is A complement? So everything that is outside A is part of A complement. Whatever is outside A is part of A complement. So you can see that A is 1, 2, 3, 4. Okay, 1, 2, 3, and 4. Okay, so what is outside A? So you can start from 5, 6, 7, and 8. Okay, so we have 5, 6, 7, and 8. So that is what? A complement. Then let's find B complement. B complement is going to be what? B complement, whatever is outside B, okay, whatever is outside B, so you can see that B is having 1, 2, 3, 1, 2, 5, and 6. So everything that is outside B, we're going to have what? 3, 4, 7, 8. Not so. That's what we have as what? As B complement. Then let's put them together. We find A complement union B complement. What are we going to have? So we're going to combine this, right? We combine the sets that we have. We combine A complement, so combine B complement. In B complement, we have 3, 4, then there's 6, 7, and 8. Okay? So that is A complement union B complement. Now let's compare the two. Let's compare A complement union B complement and what? A section B complement. Can we see that they are the same? So this is the right side. Are we seeing that they are the same? Can we confirm that? Are they the same? Is every element in the other set also found in the other set?
Yes, they're the same.
Okay. So meaning that this is true, isn't it? If we are proving using the Venn diagram, or using some steps that this is very true, very, very true. So now let's see how we prove that using what? Using the algebra method. Okay. So we have shown that this is very, very true, that A intersection B complement is equal to A complement union B complement. Okay. Now let's look at something else. Okay. So what we have, remember we said that two sets are equal if and only if they are what? Subsets of each other. So let's say we can say that A is equal to B if and only if. Now if I write I double F, that is if and only if, okay? If and only if they are, if and only if A is a subset of B and B is a subset of what? Of A, okay? So even here, what's that? A intersection B complement is equal to A complement union B complement if and only if A intersection B complement is equal, is a subset of what? A complement union B complement. Okay, so I can call this one statement 1, and what? And A complement union B complement is a subset of A intersection B complement. Okay, we can call this one statement what? 2. Now we have to prove the two statements. Okay, we have to prove them. We have to prove that A intersection B complement is a subset of A complement union B complement. Okay, and also prove that A complement union B complement is a subset of A intersection B what? Complement. So in other words, you have to prove that they are subsets of what? Each other. Okay, so let's start with statement 1. Let's start with statement 1. So if we start with statement 1, remember we're saying that A intersection B complement, okay, is a subset of A complement union B complement. Okay, then we say let X be a member of what is on the left, which is A intersection B complement. Okay, now from there it implies that, okay, it implies that if, when we say that X is a member of A intersection B complement, in other words, we are saying that X is found outside A intersection B. That's what it means, okay? If we are saying that A is a member of those things that are outside A intersection B, remember we had this, okay? And that is our A intersection B, not so. So if we are saying that A is a member of A intersection B complement, it means that A is not part of the shaded region there. Okay? It is not part of the shaded region. So in other words, we're saying that X is not a member of A intersection what? B. Okay?